We can calculate with lists by using recursive functions that follow the recursive structure of the list. One way to do this is by using the operations L.1 and L.2 to access parts of the list L. There's actually another much more readable way to write list functions. Namely, it's by doing pattern matching. In pattern matching, we access the parts of a list by writing down another list, which is actually the pattern, and by superimposing this pattern on the original list. And we use the identifiers in the pattern to pick out the parts of the original list we need. Now, this is incredibly convenient, and if this list is complicated, it makes things much, much more readable. Most symbolic languages, such as ML and Haskell and Scala, they support this kind of notation. In Oz, it's supported by a statement called the case statement. For example, let's show how we can do our sum function using pattern matching. So let me write the sum function that we did before, sum L. Now, instead of using L.1, L.2, let me write the case. Case L of nil, then 0. And then I use a special symbol, which is actually two brackets together, or h bar t, then h plus sum t. Okay, this function here will calculate, as before, the sum of the elements of a list. Let me try it. List 1, 2, 3, 4. And this returns 10. 1 plus 2 plus 3 plus 4. Notice the case statement here has two parts. We call them clauses. The first clause and the second clause. Each clause has one pattern, so the part just before the then is the pattern. So there's a nil pattern here and an h bar t pattern. When the case statement executes, it checks whether the incoming list L has the same shape as the pattern. It starts with the first pattern, so it compares L with nil. So L is 1, 2, 3, 4, and it's not compatible with nil. So then, if it's not compatible, it goes to the next clause, and then it compares L with h bar t as a pattern. And this does correspond, and to make it correspond, it will bind identifier h to 1, and then identifier t to the rest of the list, which is the list 2, 3, 4. If you do that, then you will be able to execute the body of this with the two identifiers being equal to parts of the original list L without ever using a dot operation. Okay, let me show this with a figure. So here we have an incoming list. Let's say 10, 11, 12, and I write it in graph notation. So graph notation is actually really the right way, from my point of view, to look at pattern matching, because in fact, we're talking about pictures. So the pattern here is the pattern h bar t, and I write this also as a graph. So I have here my case statement, L of h bar t, with the first clause and then other stuff. So the pattern matching here tries to superimpose the pattern on top of the list. And in this case, it actually works. We can make the pattern be equal to the list by binding h to 10 and t to the list 11, 12, nil. Okay, if we do that with these orange arrows here, and we make these two bindings here, that makes the pattern equal to the list. So we say that the clause succeeds, and we execute the body of the clause. Okay, so that's how pattern matching works. Pattern matching, of course, also works when we have tail recursive functions, and let's make this sum function tail recursive. Let's call it sum2LA. Case L of nil, then the result is A, as usual, with the tail recursion within accumulator. We have h bar t, then we have the recursive call sum2. Now we don't have to use a dot operation. We have t and h plus a. So notice how readable that the function is. So we can define this. Again, let me run it with the list 1, 2, 3, 4. And this returns 10, as before. There we go. So this is actually the way we're going to write list functions. We will use invariant programming to make it correct and efficient, using accumulators, and we'll use pattern matching to make it readable. Now, let me show some kinds of things you can do with pattern matching. I call it pattern engineering. So let me take this sum function here. Let me make a copy of it because we want to compare it to the original one. Let me now add a clause, a third clause. h1 bar, h2 bar t. Notice this clause is a little bit more complicated, this pattern. It has 3 identifiers instead of 2. And let's make a recursive call, sum2 t h1 plus h2 plus a. Okay? Let me call this function sum3. So this function also is a sum function. Now, is this function correct? Is it still correct when we add this clause? Actually, we can reason about that, and the reasoning is focused on the clause. Look at this clause. It is matched for any list that has at least 2 elements, h1 bar, h2 bar, t. So this is a list of at least 2 elements, and what it does is it does a recursive call on t, the part that's not used yet, and it adds both h1 and h2 into the accumulator. So it's correct. Okay, browse, sum3, 1, 2, 3, 4, 0, and again we get 10. Okay, so that's one example of pattern engineering. We add in a pattern to handle some particular case. So assuming we can detect this particular case and do something more optimal. Now assume now that I do something slightly different than that. I take again this pattern h1, h2, and I put it after the pattern h bar t. Let me call this function h4. h4, sum4, sorry. So sum4 again is another sum function. The first question, is this function correct? Now it is correct because the pattern is in fact a correct property of sum. It brings in the 2 elements. A second question we can ask, is the third clause here executed? When is it executed? And in fact, we can prove that this third clause will never be executed, because this third clause, it's only executed for lists that have at least 2 elements. And the second clause is executed for lists that have at least 1 element. Well, every list that has at least 2 elements, of course it has at least 1 element. So that means the second clause here, which is tried before the third one, will execute. And since only 1 clause is executed in each execution of a case at most, the third clause will never be executed.